So, hello everybody, and well, happy St. Patrick's Day. Alan was actually with us until a couple of minutes ago, and then it seems like his internet flunked out. So we have to, or I have to improvise a little bit in terms of the introduction, but at least some of you I've seen sort of participate in this before. Let me see if I can do this. Okay, I will take over the screen just for a second because I want to show you what's on as well. Unfortunately, as I said, we are improvising. This is an old version, so you can see there's Lindsay Higi here. Sorry. And well, today, Constanza. And next week, sorry, battling the technology here. Next week, we'll have Juliane Hubert talking about space weather, GICs, and MT. Alan is back. And then on the 31st of March, Colin Farquharson will talk about EM and MT data inversion. On the 7th, NASA will give us an overview of ModEM. And the week after that, on the 14th, Vladimir Pozierev on EM inversion using neural networks. On the 21st, we have Kerry Key with Mare 2D EM. So sort of a couple of weeks of modeling codes and how to use them. And then Randy Mackey on geologically consistent inversion of geophysical data, a role for joint inversion. Then there will be a bit of a break, but we might be able to fill that gap. So stay tuned for that. But definitely on the 19th of May, we'll have Malcolm Sandbridge on optimal transport and geophysical inversion. And well, as you've registered, you know that you can register for all of these through the MTNet Eminar page, and they can also find the videos and other material for the previous presentation.
Yes, this is about to start.
And just for those of you who are here the first time, there are a few controls that you have as participants. The main thing you need to know is that you should, if you have any questions, please write them in the question and answers section. We will monitor those. Usually, I think so far we've always answered them at the end of the talk. But if there's any sort of pressing issue, we can also interrupt the talk and answer the questions immediately. So I will now stop sharing my screen and hand over to Constanza. And well, maybe Alan, you want to do the introduction because as I said, I'm improvising here a bit. Okay, Alan seems to be muted, so then I'll continue. So we have Maria Constanza Manassero from Macquarie. She just told me that she's been there for 5 years. I think you finished your PhD there recently. Did I understand that correctly?
Yeah, in 2019. And since then I've been doing my postdoc there with Juan Carlos Afonso.
Yes, together with Juan Carlos. And yeah, it's going to be an interesting talk about 3D MT in probabilistic inversions, something I think most of us thought not really possible, well, until fairly recently, until we saw that it's possible. So with that, I'll hand over to you.
Okay, thank you. Can you see my screen there? Yeah, no?
Yeah.
That's all good? Yeah, the full one. Okay, well, hello, everyone. My name is Constanza, or Coti. And as Max said, I'm a postdoc at Macquarie University in Australia. So first, I would like to thank Alan for the opportunity to present this seminar and for the Eminar idea, which is, I think, is something to look forward to and that help all of us to connect with the MT and EM community in general. So I would like to give you an overview of the purpose of this talk and start by saying that most of you or some of you may know that probabilistic inversion of 3D magnetotelluric data have been impractical due to the computational cost of the forward solutions. So the purpose of this talk is then to introduce this problem, introduce our approach to solve fast forwards, and show how do we include this, use this approach to include 3D magnetotelluric data into joint probabilistic inversions for the lithosphere, and in particular, joint inversion of magnetotelluric and surface wave data. So after a brief introduction of the inverse problem and joint inversions, I'm going to talk about the basic of the reduced basis method, the basics of our approach, the structure of the code, the parameterization that we use, the sampling strategy, and the result of a synthetic example. So in case of you, in case someone is not familiar with magnetotellurics, which I really doubt, but I still would like to give you a brief introduction. So MT is a passive technique that measures variations of the Earth's electric and magnetic field in order to determine the electrical conductivity distribution below the surface. I'm gonna put the so the electrical conductivity depends mainly on the composition, temperature, water content, and melt content. And this is why MT is very interesting, because it gives us direct information about the thermal structure and presence of fluid content and melt, which are also associated with the localization of ore deposits. Yeah. So the forward problem MT means that given a conductivity model, we need to compute the electric and magnetic field at the surface of the Earth. And this is a mapping then from the parameter of the model space to the data space. Yeah, this mapping J. And in MT, then the forward is fast in 1D and 2D, but is computationally very expensive in 3D, and it's something we need to keep in mind. Yeah. Now, if we want to obtain a conductivity model given the observed electric and magnetic field, we then need to solve what is called inverse problem. And this is a mapping then from the data space to the model space. But in real scenarios, we have data with uncertainties related to measurement errors, for example. And this means that we don't have a single data point, but we have a region where the data lives. And this also means that we will have a lot of different models with their uncertainties that can be mapped from that region in the data space. And this is what we call the non-uniqueness of the inverse problem. So we also need to have in mind that together with magnetotellurics, we usually have other data sets like geoid anomalies, gravity anomalies, magnetics, gravity gradients, and seismic data. And all of these data sets are usually sensitive to different physical parameters, and therefore they can help constrain the models that explain the different data sets. This means that they can help reduce the ambiguity in the inversion. They could also help to achieve more stable solutions and increase model resolution. But in particular, the joint inversion of MT and seismic data is very interesting, as they offer complementary sensitivities to temperature, composition, and fluid and melt content that is impossible to obtain with other data sets. So this makes the joint inversion of MT and seismic something very powerful and attractive. And that's why there has been a lot of interest recently to acquire MT and seismic data together over large regions, such as the case of the AUSLAMP and AUSArray in Australia. So the main question that arises is, how do we integrate all of these and obtain models that can explain the different data sets? So on the one hand, we can integrate these different data sets by a deterministic or traditional inversion, which are based on the minimization of an error term between the forward response and the data. And it was very well explained 2 weeks ago by Doug Oldenburg. So I recommend that talk if you haven't seen it. And so this deterministic or traditional inversion have been successfully applied for inverting a large number of unknowns, and they're computationally efficient. But they're generally unstable with respect to the choice of the regularization that we have, and they depend on this choice and the initial values. So these choices may limit the information about model parameter uncertainty, and may also introduce a bias, meaning that some of the features of the true model may not be resolved because we cannot explore the whole parameter space or the model space. Also, deterministic inversions usually seek for a unique or best solution implied by the data, and therefore they are not well prepared to deal with the non-uniqueness of geophysics, inversion, and MT in particular. And as a result, they give a model based on a single physical parameter. Yeah. Oh, sorry. So on the other hand, probabilistic inversion methods are less prone to these limitations, as they provide more information about the parameters of interest and their uncertainties. So in short, probabilistic inversions are based on exploring the parameter of model space, computing forward solution for each model, and assessing how likely are these models in explaining the data. And as a result, we obtain a probability density function over data and parameters. But the posterior PDF includes then all the information about the unknown parameters and their uncertainties conditioned on the data and modeling assumptions. And therefore, they represent the most general solution to the inverse problem. In particular, the marginal posterior PDF over model parameters, this P of M condition on D, is given by the Bayes rule as follows, and is obtained as a conjunction of the available information that we have on the model parameters M, on the data, and on the informations about data uncertainties, which is contained in this condition L. So P of M, which is the probability density function over the parameters, is what is called the prior information, or what we know about the unknown model parameters prior to considering the data. And this could be, for example, structural, geological, petrological information that we have of the region, in the region of interest. The condition L is a so-called likelihood function, and describes the probability of obtaining the observed data given the model M. Yeah. So this likelihood is defined by the distribution of data errors, or distribution of data uncertainties that we choose, and this includes both observational and modeling error. So a common assumption is to assume that the data errors follow a Gaussian distribution, and in this case, the likelihood follows this form, where S is the error function or misfit, that in this case is the sum of squares, where D is the observed data, dcalc is the data that the data predicted by the forward problem, and CD is the covariance matrix that represents the data and modeling uncertainties. So in the case of joint inversions of uncorrelated data sets, the likelihood function can be expressed as a product of partial likelihoods, where each J is linked to each data set J. No? So in general, this posterior probability density function will be nonlinear and high dimensional. So it's impossible to find a simple analytical description. So in these cases, we need to approximate the posterior by sampling pointwise, using, for example, Markov chain Monte Carlo or MCMC methods. And these methods, then the objective is to sample the posterior PDF by proposing or sampling models from the model space, evaluating the posterior probability, and evaluating the posterior probability. So we do this for the whole parameter space. So one of the most common is a Metropolis Hastings method, and I'm going to show you briefly how it works. So let's say that we are in the current sample MT-1. The current sample could be like a conductivity model. And from there, we're going to propose another sample, MT, with a proposal distribution. That could be any distribution that we want. So there we are going to evaluate its prior probability and evaluating its likelihood via computing the forward problem, the forward solution for this point. Yeah. So these probabilities are summarized in this ratio that is called Metropolis Hastings ratio, where if this ratio is higher than 1, this sample will be accepted, and if not, will be accepted with probability between 0 and 1. So let's imagine that now we reject this sample, come back to MT-1, and from there we propose another sample. Again, we're going to evaluate its prior probability, its likelihood, and let's say that this ratio is higher than a random number between 0 and 1, we will accept it and continue with the exploration of the parameter space. So in order to sample the posterior PDF, then we need to repeat this process as we explore the whole parameter space and compute a forward solution for each of the samples. So as you can imagine, this sampling-based approach in probabilistic inversion makes them less efficient than deterministic inversions because they require this computation at millions of samples. So then this becomes very impractical when the actual forward problem is very expensive to compute. So in this way, probabilistic inversions provide extensive information about the unknown parameters. And as a result, and the results are almost independent from the initial values. They're therefore global and robust too. But as I shown before, in order to perform the probabilistic inversion, we need to run millions of forward solutions. And this limits application to problems where only fast forwards are available. And since 3D empty forwards are really expensive, they had never been used in a probabilistic inversion before. So how do we compute fast forwards and include 3D empty into joint probabilistic inversions? So in the last years, some method and strategy has been proposed for reducing the cost of full forward solutions. And the general idea behind all of these methods is to build an approximation, which is called the low fidelity or surrogate model, and that can be used instead or combined with the expensive full forward or high fidelity solution, what is also called. So this combination is usually very beneficial in, for example, in the context of probabilistic inversions to estimate the posterior PDF. Yeah, so here we use reduced basis methods to compute fast forwards. And I'm going to show you briefly how it works too. So for solving fast forwards, we use a very simple idea, which is computing approximately or surrogate solutions by combining meaningful forward solutions, meaningful full forward solutions. Yeah. So a very simple way to explain how reduced basis works is by imagining that we want to generate a color, any color. And one way will be to use the RGB color palette where red, green, and blue are the primary or basis colors. Yeah, so by combining different quantities of them, we can generate any color that we want. Let's say this light blue, for example. So reduced basis works in the same way. In the case of empty, we have some bases that are full forward solutions at certain conductivity models. And for any new conductivity model, we will find its solution or its reduced basis solution as an approximation of the basis that we have. So let's imagine that during the MCMC inversion, then we start from a 3D conductivity model. And we first are going to compute the full forward solution since we don't have any more bases. And as we explore the parameter space, we take a random sample of random conductivity 3D model, and we're going to evaluate if this model is different enough from the previous models. So if it's similar up to a tolerance, we then will compute its reduced basis solution using the basis that we have stored, yeah, the previous basis. So now let's say that we go to another sample, we evaluate this and say like, well, no, it's very different from the previous one. So in that case, we will compute the full forward solution and store this base as a new base in my basis space. So now again, we go to another random sample. If when evaluate this, we say that is not so different from the previous one, we then now compute the reduced base solution with the two bases that we have as a linear combination of these two bases. So this means that when we are performing the 3D joint probabilistic inversion and we need to compute the forward for empty, we don't need to compute the expensive forward, but we instead seek for a solution as a reduced basis solution, as a combination of the previous bases. And this is super fast. So solving the 3D empty forward means that given the conductivity model in the distribution in the subsurface, we need to obtain the electric and magnetic field that satisfies the Maxwell equations and boundary conditions. And we need to do this for each frequency. Yeah. So using the secondary field formulation of Douglas et al. And the absorbent boundary conditions of that were defined by Shin in 1997, the empty forward problem in 3D reads as follows. And we obtain high fidelity or full forward solutions by an optimized version of the finite element code of Zisserman and Santos in 2000. That after we discretize this follow linear system of equations, where K is the stiffness matrix.
It seems that we are having connection
Stiffness
problems.
matrix, sorry. Offside. Oh yeah, sorry, can you hear me now?
Yeah, at least on my end, you were interrupted and the video stopped. So maybe you just want to go through this slide quickly again, because at least for me, parts were missing.
Okay, sorry. So I start all from this. Okay, so I go back then. So the 3D empty forward problem reads as follow. We're using the secondary field formulation and the absorbent boundary conditions defined by Shin in 1997. And we obtain then high fidelity of full forward solutions of this forward problem using an optimized version of the finite element code of Zisserman and Santos. So after we discretize the variational formulation of the forward problem in terms of the finite element shape functions, the equations are converted into this the following linear system of equations, where K is a sparse matrix that is called a stiffness matrix, like the finite element stiff matrix, and F is the force vector. And here the size of this matrix K is NFE times NFE, which is usually very large, where NFE is the number of degrees of freedom. U is the vector containing the unknown coefficient for the electric field in the whole domain. And our objective then, when we solve the full forward, is to solve these equations to obtain U. Yeah. So we do this using the parallel solver MAMS. Now, the idea behind the reduced basis method is then to seek for a surrogate solution as a projection onto this and RB way smaller than the dimension of K. So we generate this reduced basis space per frequency and field orientation and basis vector U, UH here, which are a full forward solution from of this linear system of equations. Yeah. So the surrogate solution URB is then sought as a linear combination of the vectors of the bases in URB, which are put together in this matrix of reduced basis matrix, and a coefficient, a vector of coefficient A, which are the coefficients that will be multiplying each basis in the linear combination. So the reduced phase, so for this we need to find, actually our unknowns now are the vector of unknowns A. So this is done by solving this linear system of equations now of a smaller size than the previous linear system of equations. Yeah, so when we solve this linear system of equations for A, we come back, multiply by the reduced basis matrix and obtain the reduced phase solution for that frequency and field orientation. So in order to assess the accuracy of the surrogate, we compute the following relative error. And we are going to set the surrogate solution if this relative error is smaller than a prescribed tolerance. And otherwise, we will then compute the high fidelity solution for that frequency and field orientation and add this as a new basis to enrich the corresponding space. So how do we implement the reduced base approach for the joint empty and surface waves inversions then? So this is a scheme of the complex structure and the different levels of parallelizations that is used in our code, which is written in Fortran. And in gray, we show the CPU parallelization, and in orange, the solvers and subroutines that are used to make it computationally efficient. So the computation of the 3D forward is then parallelized per frequency and per mode, and this together with the algebra of the reduced basis method, it's what is gives us a time reduction from tens of minutes to less than a second, or approximately a second per simulation. Yeah. So how do we parameterize our models for the joint empty and surface waves inversion? So a key difficulty in the joint inversion of two or more geophysical datasets is how to consistently define the relationship between model parameters. So in the case of joint inversions of empty and surface waves, the primary parameters that are controlling both the seismic velocities and the electrical conductivity in the mantle are temperature, bulk composition, and pressure. But also, the electrical conductivity is highly sensitive to hydrogen content and localized melt or fluid pathways. So then the model parameterization that we choose needs to allow us to accommodate the primary or background parameters that will simultaneously control the seismic velocities and the conductivity, and those variations that are responsible for conductivity anomalies over the background. Yeah? So let's imagine that we have the following large-scale model with the background conductivity structure and localized conductivity anomalies. So with all things in mind, and given our particular interest in imaging the lithosphere, we propose a mix or combined parameterization of the conductivity. And this is a first parameterization that uses the LAB depth of 1D columns to represent the background of first order conductivity distribution related to the temperature, pressure, and composition. And this parameterization will, of course, provide the background seismic velocity field. So a second parameterization will be useful to represent the anomalous conductivity over the background, where the parameters here are conductivity nodes, this white dot, randomly located within the inversion volume. So the anomalous conductivity field is then obtained kriging. So the sampling strategy is then tailored to take advantage of the differential sensitivities of the surface waves and the MT to the conductivity and velocity structure of the lithosphere. So with this in mind, we subdivide the MCMC inversion into 4 main stages. The first stage aims to constrain the background conductivity and velocity fields associated with the first order temperature structure defined by the LAB depth. And by this stage are the LAB depth, so 1 LAB at a time, using a proposal Gaussian distribution, and we'll first evaluate the the likelihood of this model using the surface wave forward. And if this is accepted, we then proceed to evaluate the likelihood with the MT forward. This is what it's called a cascade Metropolis algorithm. So in stage 2, over the background, and for this, we're going to randomly choose to sample the LABs or the conductivity nodes. If we choose to sample the LABs, everything is going to be the same as the stage 1. And in the case of the conductivity nodes, we are going to select N nodes, randomly selected in the whole parameter space with the same probability to be chosen. And we are going to propose a new conductivity value for those nodes using a log normal distribution centered on the value of each node. And we are going to reevaluate the likelihood of this model with the MT forward only. So once we have enough information for this for the samples, meaning that we have information about the correlations, we can incorporate adaptive strategies to efficiently sample the full parameter space. So for the LAB, we're going to compute a multivariate Gaussian proposal distribution. And once we have this, we're going to sample n LAB at a time, and propose for all of them new depth values for using this proposal. And in stage 4, we do the same for the conductivity nodes. So in the following, I present a synthetic example for a large-scale lithospheric model. The data, the synthetic MT data are the full impedance tensor computed for 12 periods between 3.2 and 10,000 seconds at 400 stations. The data errors are assumed to be normally distributed with standard deviation of 5% of the maximum amplitude between sec x and sec xy for these two components, and the same for the other components, sec yy and sec yx. So the surface wave data are the normal model of the Rayleigh wave phase velocity for periods between 15 seconds and 175 seconds, computed at the same location of the MT stations. And again, we assume normally distributed data uncertainties of 1% of the velocity in meters. The surface waves and MT misfit are computed as follows, where STA and N pair are the number of stations and periods for each dataset. Dij and Gij are the observed data and compute data with the surface waves and MT forward in particular, and for stations I and period J. And STDij is the standard deviation for each data. Here, the factor in that is a total number of MT data for station and frequency. So let's say now that we're inverting for the whole impedance tensor, we will have the real and imaginary parts of each component. So this means that we have 8 data. So this factor, 1/n that, is used here to ensure that both data sets have similar absolute contribution in the joint inversion, in the misfits. So the inversion area is subdivided in 324 columns, and we also use 1155 conductivity nodes. This is a total of around 1500 parameters. And the prior for the LAB are uniform distributions defining the range of ±70 kilometers centered on the actual true value. And the proposals used in the first stage are Gaussian distributions, as I said before, with a deviation of 20 kilometers. And for the conductivity nodes, we use Gaussian prior distribution centered on the background conductivity value with a standard deviation 1.5 in logarithmic scale, and the initial proposal distribution and log normal with standard deviation of 0.9. So the initial model then is, the starting of the MCMC inversion has a flat lab at 180 kilometers depth, and we ran a total of million simulations for 12 frequencies using 2 processors per frequency. And we also use variable tolerance. This means that we use a more relaxed tolerance of 0.068 for the first 150,000 simulations, and a more tight tolerance after those that number of simulations. And the inversion took, 14 days with an average of 1.2 seconds per simulation. So after a million simulations, we obtained then full posterior probability density function over the parameters of interest and data 2. And for example, here we show the marginal posterior PDF for 30 LAB depth, where it can be seen that the mean of the posterior PDF, the shown in blue histograms, is close to the real value shown in green. In red, we have the initial values, and in blue, the bounds of the prior distribution. The same, we can show the marginal posterior PDF for the nodes, where it can be seen that some of them are bimodal distributions, and this is something, very important information to have from the probabilistic inversion. But with all this information, we could also be interested in obtaining for example, the maximum a posteriori and the mean conductivity models of the posterior PDF. And here we can see that the background conductivity structure and the location and volume of the anomalies are very well resolved. Yeah? As another example of the information about the parameters and uncertainties we can obtain by exploring the posterior PDF, we plot the lower bound and the upper bound of the 95% confidence interval. And a little bit more about the same, this video showing the isosurface of the mean model obtained after immediate simulations, and the same for the, that was the best model, and this is for the mean model, sorry. Yeah. So one of the nicest ways to explore the posterior PDF, at least for me, and show the variability of the models that are likely to explain the data, is to take random samples from the posterior PDF. So here we have depths like mean and the lower and upper bound of the 95% confidence interval, and 5 random samples, which are taken as the mean of 10 random samples from the posterior PDF. Yeah. So as expected, all the features that are well resolved by the inversion are consistent or persistent throughout all these random models, but features that are poorly resolved are more present more variability. Yeah, which is also something that we expect to have. So as an example, the posterior PDF of the surface waves are these ones, where we have the data and data errors in green, in blue the forward solution for the initial model, and the full posterior PDF. And we can see that all the dispersion data points are contained within 1 standard deviation of the posterior PDF. The same for the MT. Here we have the real imaginary part for all the components of the impedance sensor. And we can also plot these in apparent resistivity and phase. Yeah. So lastly, I would like to show the misses for the MT and the surface waves for all the simulations, and the basis number for 6 of the 12 frequencies. So in all cases, you can see that the rapid increment in the basis size is seen for the first 100,000 simulations, which correlates with the rapid decrease in the misfit, in both misfits. So this is a combination of 2 factors. And for instance, the starting point of the inversion is far from the high probability region, and then the initial proposal distribution is not optimal. So as the MCMC algorithm starts sampling the space in this first stage, the jumps or the steps are usually very large, and this corresponds with conductivity models that are different from each other. So this means that we need to compute the basis to enrich the surrogate and in order to produce accurate solutions within the regions. No? So we can observe that after 400,000 simulations, the number of bases reaches a plateau or saturation of the surrogate. And this means that the chain has reached the high priority regions of the model space, but also that the reduced basis surrogate has been enriched enough to provide accurate solutions within those regions. So the results from this example demonstrate that the joint probabilistic inversion of surface waves and 3D MT data is a practical option using a few computational resources that it succeeds in identifying the LAB, the background conductivity structure and anomalous features, and that we produce well-behaved posterior priority distribution that give us a measure of the uncertainty and correlations between the parameters. So these results are described in our last two publications that was already published, and the second one is in review. And we are currently applying this approach to field data from Ausland and the Aus array in southeast of Australia. So as a conclusion, I would like to say that our strategy RB+MCMC combines a parallel structure, reduced basis methods, and adaptive strategies for both the MCMC and the surrogate model. And this is what allows us to obtain a fast forward for MT. Yeah. So this, together with an efficient parameterization of the background and the conductivity anomalies over the background that takes advantage of the differential sensitivities of MT and surface waves, results in the first probabilistic inversion, joint probabilistic inversion of MT, of 3D MT and surface wave data for imaging the electrical conductivity and velocity structures in the lithosphere and sublithosphere upper mantle. Future work includes performing then joint probabilistic inversion using real and empty data, and incorporating a more efficient sampling strategies and parameterization, such as the transdimensional scheme or parallel tempering. Thank you so much.
Yeah, well, thank you very much for that. That was very interesting. So we are open for question now. We already have one question in the chat, but while other people are typing, I'll take advantage of my unique position and ask a first question. So I find it very interesting your way to deal with heterogeneity with these sort of random sample points, and I think it's a very nice idea. Now, for real data, or your focus is on the mantle, yes, and I think your model was mostly sort of 60 kilometers and below.
410, like lithosphere and upper mantle, yeah.
Yeah. So in my experience with real data, though, a lot of our sensitivity, even when we look at long periods, let's say 100 seconds or 1,000 seconds, is actually in the crust. And of course, the crust is highly heterogeneous. So how do you deal with that? I mean, you showed that you are working on real data. Can you comment on that?
Yeah, sure. Yeah, so that's a really good question, and it's something that happens, and we need to consider 100% though, because the crust, so like the conductivity in the crust affects everything that we will see underneath. So we first, right now I have actually the real data that I'm using now, and the models that I'm producing. What I use is using conductivity nodes, all these in the crust too. So we have the freedom and the the chance to fit all the structure, the conductivity structures that are in the crust too. And in terms of the seismic velocities, we have layers in the crust that also are parameters. So we can change the seismic velocities and the seismic velocities in the crust. And then on top of that, we have the conductivity, node conductivities that are not over the background, but are like absolute values in a sense, not relative values. So we can assign any conductivity value that we want there and interpolate this in the whole crust. I don't know if that answers.
Yeah, sure. And I mean, while you were sort of explaining this, I got sort of a related question, because I can imagine that this must be also a challenge for your reduced basis approach, because if you have highly heterogeneous structure, you sort of immediately go out of sort of any linearity. So have you seen that?
And that's exactly what happens. Of course, so as you can see from the talk, or I guess it's also your question, the more complex is your model, the more bases you're going to need to compute, in a sense, no? Because you need to start sample like way more different models, and the complexity of the models also requires that you have more solutions, or that as the MCMC finds those paths to the high probability region, you're going to find, you're going to accumulate bases, you know? So this is like one of the main drawbacks of the, or bottleneck, probably the code itself, that is like, yeah, if the model is more complex, we will have more bases to explain those solutions. And this is again something that with all the computational resources that we have now, I can expand and do this code in that terms more efficient too, in a sense. But the only thing that is like, we will create more bases, and that will be the only correlation that we will have with a more complex model, in a sense.
Okay, yeah, well, thank you. I don't want to sort of abuse my power.
No, it's good, yeah.
So let's turn to the questions from the audience. So we have Pavel Alexandrov. Macroscopic electrophysical rocks possess anisotropic and moreover the capillary system of electrical. Sorry, this is a longish question. Leads to bi-anisotropic models of the medium. Okay, in this case, the Tikhonov approach loses its effectiveness. Numerical methods for solving direct problems face mathematical and computational problems. Okay, now comes the question: are there any ideas for formulations of inverse MTZ, I think MT problems, and geophysical problems in general?
I quite not understand the question, sorry.
So I think, I mean, I would say what you're doing, right, is a new
exactly, yeah. So it's trying to
compared to what many
because the Tikhonov approach, in a sense, is regularization. Also, I guess what he's saying, like, we lose effectiveness because there's so many other parameters that needs to be taken into consideration. And again, if we consider all the things in the probabilistic inversion, in this case for this type of parameters or things that we are interested in seeing, probabilistic inversion will totally be applicable to that. And also reduced basis method are completely fine to be used in a smaller scale too, no? It's all about adapting the mesh and everything that needs to be done. Yeah.
Yes. Okay, we have a few more. So David Goldak, how effective do you think your Monte Carlo search is, given that we are usually dealing with poorly estimated error bars with real field data? I.e., do you have to guess your error bars as well? 5%, well, that's 5%, 10%, etc. This would add another.
1 second. How effective do you think your Monte Carlo search is giving?
So
poorly estimate. So do you have the? So if I understand the question well, actually Monte Carlo and probabilistic inversions are pretty much made to deal with the error bars that come from the data. So this is what we take use of the information that comes from data with the uncertainties that come from the data, and we're gonna the MCMC will give all the models that are likely to explain the data with its uncertainties. So if we have, of course, data with a lot of uncertainties, that because they have that uncertainty, we will have a larger range of models that will explain the data, because this is natural, no? We cannot force our inversion to give only one model when we actually have a lot of models that will explain that, will fit that data with the uncertainties. So in terms of the level of the error floors, this will add another level of looping and such. The last part I don't quite get it. This would add another level of looping to search the model space.
No, so I think the point I'm trying to make is, and this is something I see with inversion as well. So you get your data and you get some errors with those data, but then if you have seen a few data sets, you fairly often know that okay, these errors are not real. They're not representative of actually what the errors are. So yes, your MCMC if you tell your MCMC my uncertainty is X, it will give you a search or a range of models, but you actually don't know this X. I think that's the point. Yes, so you have to make a decision whether.
Yeah, well, yeah, and that's something that I think we all have the problem, no? Because when I think that's the problem when working with real data, I guess. When I work with real data from NT, for example, and it's like, well, some people, when they process that, they put this error, they do this combination of errors, the error floor, and yeah, it's something that is very subjective. So I would personally love to just use the errors that comes with the data per se, no, because that's what is observing the field, and we cannot do much more than that in a sense. And so these error floors, that is something very common in MT, and actually I taken that from the MT community too. And it's like, okay, well, if the errors are very, very small, we are not gonna give them so much credibility in a sense, because we know that it's not so true. So let's relax here a little bit more, put an error floor that is bigger than those errors. So then we actually don't bias our inversion too in favor of models that are gonna fit that data with that small error, no? So I think what you're actually doing is, well, giving more freedom or expanding the range of models that you actually are gonna fit your data, giving error floors that are bigger than the errors that you actually have, no?
Yeah, and I think it's an interesting problem. It's a problem
for sure. Yeah, because it's true, no? In a sense, the assumption that you have on the data errors and what you assume as a standard deviation, I think, is where it actually is gonna modify the shape of the likelihood function. That is what you are computing for each sample, and what it actually determines your how wide is your posterior probability density function in a sense, no? So I guess that's more something that to work together to, okay, what if we have the real data and it's good, perfect, let's use those errors, no? And if we have very small errors, which is unreal, then it's a matter of, okay, the people that is used to work with the data to put like, well, let's expand the range, no, of and give more error and error further is bigger than the ones that we have.
Yes, but I mean, my gut feeling would be that certainly, unless you do something very strange to how you assign the errors, increasing the errors in general, yes, will change the shape of your posterior, but relatively speaking, it will sort of stay the same. So that you will see
it will be more wide. Yeah,
resolved, and this is well resolved, and you can't sort of put too much trust in the absolute width of that Gaussian, for example, to say, okay, I have plus minus so many ohm meter resistivity, but the relative information will stay the same.
And yeah, and in a sense, if everything is well posed, the mean value of those posterior distribution will also be the same, no? So
yes.
yeah. So yeah, but it's an interesting thing, and I think it's something that conditions the inversion for sure.
Okay, we have another question from Darcy Codell. Do the conductivity nodes change both position and resistivity as the simulation progresses, or are they fixed in space?
Yeah, so for now they are fixed in space, and they only change the conductivity value. But something very interesting, and I think is going to be our next step, is to implement transdimensional scheme with Ray, that he's from and working in Geoscience Australia. And this will be actually what we need to do probably, because that will make the parameterization or try to find the best parameterization in terms of like the trade-off between how many nodes do we need for this particular model, in a sense, no? So, and to find more parsimony representation, in a sense, parsimonious representation. So that can be totally possible, and everything is kind of set, because I'm using Kriging interpolation, which is the base of Gaussian processes. So everything is set to that direction. So yeah, that will be the next step. But yeah, really good question.
Yeah, I mean, that will be interesting. Although I wonder, these transdimensional algorithms, how well they deal with high dimensional spaces, because I think so far they've always been applied to problems with, you know, a dozen parameters.
Yeah. Well, I don't know. We did some tests. Ray did some tests, and we haven't done it in the MCMC, but for the models that we were using, I think the average of nodes were like around 80 to represent the structures that we have for this size of models that we're using. So the thing is, it depends of the model that you have and the data that you have. How because of course, if you have data that is not constrained in anything in the region, there you pretty much can put whatever that the data won't see anything there, you know. So sometimes it's that compromise that, okay, how many nodes we actually need to represent the structures that we have, but also how close or how close to each other, or which is the relation between them. No, so that's something that is impossible to know a priori, and a transdimensional scheme will benefit this.
Yeah, no, it will certainly.
So yes, yeah, but in terms of the high dimensionalities, it depends. I think we need to do some tests and try to work on that more and see like how does it work, because it would be super good if we have that, to reduce the dimension in our parameter space too.
Yeah, of course, potentially you can then get rid of unnecessary parameters.
Yeah, exactly. Yeah.
Okay, that seems to be it. I mean, we have sort of a few less participants than usually. I think the time, Australian time, is sort of a bit strange for sort of certainly Europeans. Like I'm going for this.
Yeah, I know. What time is it? Like 8 p.m. No, there for you. Yeah.
No, it's 10.
No,
10
p.m. Yeah. Yeah.
So I think sort of other people then decided that they sort of maybe need a bit of rest and maybe catch up on YouTube.
Exactly.
A little bit later. So, well, thank you very much for the discussion.
Well, thank you. Yeah, thank you for hosting my talk too.
Thank you everyone for attending. And so next week,
Juliane
Hubert talking about GICs, MT, and space weather.
Mm-hmm.
Okay.
Yeah, I just want to say that if you have any more questions or anything, feel free to send me an email or something. That would be nice to hear your comments and questions too.
Yes, and your email is in the lower right corner of the slide.
Yeah.
You can be found very easily. Okay.
Yeah, exactly. Okay. Bye-bye. Thank you.
Bye.
Bye-bye.